Good afternoon everyone and welcome to my presentation. Let me introduce myself. My name is Vitaly Slobodyan. I am PhD student of computer science at Khmelnytskyi National University, Ukraine. The subject of my presentation today is myocardium segmentation using two-step deep learning with smoothed mask by Gaussian blur. Our research consists in detecting and segmenting the left ventricle myocardium. The first challenge of this task is providing high-quality segmentation, because when it comes to medical tasks, it's important to provide the best accuracy possible. So it's always actual to work on improving accuracy. And the second challenge in healthcare diagnostic is the black box nature of AI algorithms. So we keep in mind increasing the trust and transparency in AI-based systems. Here on this slide you can see a simplified scheme of the proposed method. It has two stages, localization and segmentation. On the localization stage, we are looking for the area of interest. We try to find the area where myocardium is located and cut the image to have only this area. On the second stage, we are actually looking for the certain myocardium segment and do some post-processing to improve it. As input, we have MRI image, and as output, we receive myocardium segmentation mask. Let's talk in more detail about each of these steps. The first stage is localization. For studying localization model, we use dataset which consists 2,169 images taken from 150 patients. We split the dataset for testing and training in proportion 20 and 80. Then we prepare each image for studying. For such network, it's important to have images with the same number of channels and same size. So here we cut image to a square and resize it to 250. The best size was found in experiment where we compare effectivity of model using different image sizes. As you can see from chart, size 250 shows the best dice value. Then we train our model. For this we used pre-trained network ResNet34 and popular Python library FastAI. Studying goes in two stages. First optimal learning rate is found and run training at high speed for 10 epochs. Then the optimal learning rate is reformed again and running new training for 10 more epochs. This approach to training helps to increase the accuracy of the model. The second stage looks pretty similar. In this stage, for studying segmentation model, it is used the same database, but with another mask. We will talk about them later. And we split dataset for these three parts. It's for training segmentation model, for training linear regression model, and for testing in proportion 60, 20 and 20. Then we prepare each image for studying the same way we did it for the first stage. The only difference is that the best size for localized image is 60. Training segmentation model is absolutely the same. Since the model is trained using resized images, it is necessary to return the image to its original size before testing it. However, usual resizing causes lots of loosed details and may cause some artifacts. It of course has effects to the final result. To solve the described problem, we propose to use blurring technique to smooth transition between pixels and create more natural and smooth effects when resizing images. On this slide you can see Gaussian blur formula, but the most important thing here is sigma parameter that affect the degree of blurring. The choice of the sigma is important to achieve the best resizing result, but best value for it depends from image size, so that's why we use linear regression to automatically select the best value based on the image size. On this slide you can see the effect of such improving. On the left side is predicted mask and on the right side is improved mask. On this slide we can see how all these steps fit together. But let's talk more about dataset. The original ACDC dataset has label for right and left ventricle and myocardium. you can see the original mask on the first image. Using the original dataset, we create two other datasets, one for the first stage, and the left ventricle and myocardium segment were united. And the result mask we call region of interest. It is presented on the second image. As for second stage, we are not using left and right ventricle segment mask during training, so this information is redundant and we can remove it. This modification is aimed to reduce information noise. It has a positive effect on the quality of studying model. This mask is presented on the last image. During the training and testing most of the model using the original dataset, it was found that some masks have minor inaccuracies. It can be either an accidentally marked part of the image or a missed part of the myocardium. On this slide you can see one example of such problem. The first image is the original mask, on the second image is updated mask, and on the last image you can see the modification difference. We can see in the area A the big part of ventricle which was marked as myocardium, and in the area B there is a part of dark tissue, it's part of myocardium, which was missed. It's pretty obvious that such inaccuracies have a big influence to the studying model, so all marks in the dataset were received and reviewed, and some contours were improved with practical cardiologist. And last but not the least, the dataset was filtered. Some images have poor resolution or poor quality in general, which negatively affects the performance of the model. In addition, the original dataset is not focused only on the myocardium, so some images that, for example, have sense with right ventricle segments may not have any value in the study of myocardium. The dataset was filtered using criteria you can see on the slide. So the first reason to remove image from dataset is partially or completely not visualize the myocardium. Second reason is too small myocardium segment. Third reason is partially or completely not visualized left ventricle. And the last reason to remove image is low to or high brightness level. That's all about dataset. Let's now talk about results. On this slide you can see comparison of the result of our different approaches using updated dataset. The first experiment tests model without localization using all mask labels provided in the original dataset. Then we use updated dataset with only myocardium mask label. Then add localization step. Then post-processing and resize image before testing. And in the last first experiment, we test model with localization using Gaussian blur and resize the mask. As you can see, each improvement increases quality, and altogether it shows dice value 0.955, which is pretty good result. On this slide is comparing the proposed approaches with other approaches using the original dataset. From the provided table, we can see that the proposed two-stage segmentation approach shows a slightly lower result compared to the winner of the AC/DC segmentation. Also, the additional improvement in mask accuracy using the Gaussian method increased the result by 1%, but it's still lower than the best described approaches. Then fourth, while the mask improvement using Gaussian blurring demonstrated increased myocardium segmentation effectivity, the segmentation method requires further refinement and enhance the final result. In conclusion, our approach proposed the new competitive method shows significant improvement with the updated dataset, shows good result compared with other approaches using the common dataset. Further research will be directed at improving the accuracy of model and using the obtained result to improve existing solutions that detect areas with inflammatory tissue in cardiac MRI. That's all from me. Thank you for your attention. If you have any question, please contact any of us using the email on the slide.